class. Yeah, whoever is ready, just go ahead.
I'm presenting problem 19. So 7 different gifts are to be distributed among 10 children. How many distinct results are possible if no child is to receive more than 1 gift? So I just make 10 children to be a different group. This first 7 group would be represented by 7 different gifts, and the last group would be children who did not receive their gift. So it will be 10 factorial divided by 1 factorial 7 times, and then 3 factorial. This represented by children who did not receive their gift, and that would be this one.
Yeah. Nice. Anyone has any questions? Okay, thank you. Next one, who's ready?
Hi, Professor.
Okay, yeah, go ahead.
Okay, I'm going to present the question 17. A dance class consists of 22 students, of which 10 are women and 12 are men. If 5 men and 5 women are to be chosen and then paired off, how many results are possible? So in this question, it's a combination. So first, I calculate the ways to choose men, which we need to in 12 men, we need to choose 5 men. So it's 12 choose 5 equal to 12 factorial divides 12 minus 5, which is 7 factorial times 5 factorial. Then make a calculation, I got 792. Then second, I calculate the ways to choose human, which is in 10 human choose 5 human. It's 10 choose 5 equal to 10 factorial divides 10 minus 5, which is 5 factorial times 5 factorial. Then make a calculation, I got 252. Then we need to pair them, and 5 men and 5 women. We can pair 5 pair. So it's 5 factorial. Make a calculation equal to 120. Then final need to times these 3 together. We will get the final answer.
Great. Great. Anyone has any questions? Thank you. Yeah, nice. Who's next? Okay. Someone wants to use a whiteboard? Oh, sorry, why the whiteboard is on and off? Someone is trying to use a whiteboard? Okay, who's going next? Okay.
Hi, Professor.
Let me make a present also. Yes. So Catherine.
I'm presenting 23.
Okay.
Okay, consider the grid of points shown at the top in the next column. Suppose that starting at the point labeled A, you can go one step up or one step down to the right at each move. So like for this question, since and there's a hint saying you must take 4 steps to the right and 3 steps to upwards, so that is like according to this grid, we're going 7 steps in total. We're using permutation for this question, since like we also go 3 steps to the right, no, and then 3 steps upward. We're using permutation as 7 steps factorial over 3 factorial times 4 factorial. That gives us answer to a total of 35 different paths from A to B are possible.
Mm-hmm. Yeah, that's an interesting question, huh? Yeah, nice. Okay, so this is Catherine. All right, thank you, Catherine. If anyone has any questions, just jump in. Yongxin, that's okay, no worry. Okay, whoever is ready, just go next.
I can do problem 27.
Okay, Tom.
So this is expanding this binomial.
Oh, okay.
So, okay, it's really hard to type.
Yeah.
Okay. It's the power of 4 here. So to do this, we just use the binomial expansion theorem. Where
Binomial? Okay.
So we have, so each coefficient is going to be.
We learned the multinomial, right? We learned the multinomial theorem.
Right.
Since you are doing on whiteboard, can I add something to it?
Sure.
Add a -1 to it, or +1. Let's make it easier. So 4x minus 3y plus 1 raised by 4. So as a review to previous class.
Okay.
Remember, we go from 0 to n, 0 to 4.
Did you say plus?
+1. I can do that for you. If you
Did you say that?
yes. Yeah. This one, can we delete? I think we can delete this. Yeah.
Okay.
Remember, each term, the coefficient go from 0 to 4.
Right. So the first coefficient is 4, choose 0.
Yeah, you have to think of the permutations of 4. You have 3 spots. The 3 spots has to add to 4. Maybe you have 4, 0, 0, right? 0, 4, 0, 0, 0, 4. Then maybe, so let's start with 4. Then you can start with 3. 3, 1, 0, 3, 0, 1. Let me type in the chat. The coefficient. I mean, not the coefficient, the exponent. You know what? Let me. Do you remember the multinomial theorem?
Yeah, so the first term in the summation would be like this. Then we would have to, the second term would be n minus k.
Let me show you the multinomial theorem. It's different from the, what do you call it? Binomial.
Okay.
Yeah, let's review. So it's
Okay.
good for everybody to review. So let me, for temporarily, let's go to the textbook. I actually need to review myself. Just to be, okay, multinomial theorem. Okay, this is the proposition. Multinomial theorem is it before or after? Or before, yes, here. Okay, so you see yours is raised by 4. So these are 3 things raised by 2. So you could have the first position to be 2. So you have 2, 0, 0, 0, 2, 0. You see this? Then you could have 0, 0, 2. Then you start with 1. For you, let's change yours to be 3. Oh, you know what? Let's change yours to be 2 to make it easier. So you have this 1, 0, 1, 0, 1, 1. And then the coefficients, because this is, remember, this is just n1, right? This is n, this is n1, n2, n3. n1, n2, n3 always adds up to 2, always adds up to the degree. And then x1 is corresponding to with n1, x2 corresponding with n2, x3 corresponding to with n3. You're good now?
Mhm.
Sorry to put you on the spot. This is an example 4D pair with question 27. Someone is going to present. Oh, okay. All right, someone is going to present. All right, so, okay, you finish your binomial then. Tom, you can finish
Okay.
your binomial.
Um,
Okay.
So I'll just say it because it's gonna take too long to type out.
Yeah. So it's better, Tom, next
Yeah.
time just to load up your homework.
Yeah.
All right. Yeah, to do that.
Okay. So
Typing is very difficult. Yeah.
yeah. So for the binomial expansion, basically the first coefficient is 4, choose 0, and then the x term will be 4 minus 0 for the power, and then the y power will be 0. Then the next part
Oh,
of the
the
summation,
whiteboard disappeared.
yeah, it's a 0. And then
Oh.
then you do 4, choose 1, and the next power will be 4
Are you
minus 1.
typing in? Are you typing on the whiteboard?
Oh no, I'm just saying it because it would take too long. Yeah.
Oh, you know
And
what? No, I don't. You cannot just by saying it. You have to show
okay.
it too.
Okay,
All
yeah.
right.
I'll upload it next time.
Okay. All right. Thank you, Tom.
Okay.
Okay.
Hi.
Yeah. Next one.
Hi. I'm doing number 15.
Number 15. Okay.
Let's consider a group of 20 people. If everyone shakes hands with everyone else, how many handshakes take place? So the answer would be NCR.
Right.
And choose R. The number of people would be 20, and handshakes would be 2, because one handshake equals 2 people. So we would start with 20 factorial over 20 minus 2 factorial, or 20 choose 2, same. And the answer would be 190 handshakes.
Okay. So is it 20 times divided by 2? Yes. Okay. Yeah.
Okay.
Okay. This is Andrea. Okay.
So I'm going next.
Okay.
Professor, my screen is visible.
It's, yeah.
I'm going to present question number 18.
Okay.
In this question, student is going to sell 2 books from 6 math, 7 science, and 4 economics books. So we have to find how many choices are possible. There are 2 options. Both books are to be on the same subject. Then for the one, we have to choose 2 books from the same subject. So for math, we have 6 total, then 6 combination 2. For the science, we have 7 total, so 7 combination 2. And economics books, for the economics books, we have 4 total, then 4 combination 2. So only one of the above 3 options is possible. So we have to sum all the combinations. And when we expand the combination formula, so we get that 6 factorial over 2 factorial, 6 minus 2 factorial plus 7 factorial over 2 factorial, 7 minus 2 factorial, plus 4 factorial over 2 factorial, 4 minus 2 factorial. So when we sum up, we get 42 for the part A.
Great. I want to mention, hold on 1 second. How do I call your name? IQRA. It's a, how do I pronounce your name?
Equatoric.
So it's Ikara, your
Yeah.
first name.
Yeah.
Ikara. Okay. Ikara. So this is such a good point. Only one of the above 3 options is possible. So here, everybody pay attention to this. So usually, you know, we choose out of the 3 choices by counting principle, we multiply them. But however, this
Yep.
is a condition here. So
Yes.
this is such a good point here. Yeah. So
Yes.
that's why we add. Why we add? Because only one of those. Okay, great.
Yes.
Okay, keep going. Thank you.
For the part B, the question is the books are to be on a different subjects. Then we have to choose one, mean to say we have to choose different books, combination of different books. So one math and science books for we have total 6 and we have to choose one. So 6 combination 1, and for the science we have total 7. So we have to choose one. So 7 combination 1. Similarly for the science and the economics book we have 7 combination 1, 4 combination 1 for the economics one. So one economics and the math book we have to choose total 4 and 1, and economics 6 and 1. So total number of options we have, because we have to choose 2 books, that's why we have the combination of 2 subjects. So we have to sum up all the combinations we find above. So then we sum up. So finally we got the answer of 94 when we expand the formula of combination.
Okay, great. Thank you.
Thank you.
Yeah, good question to present. All right, next one.
I'll go next.
Okay.
Can everyone see my screen? I'm doing question 27.
No, I don't see your screen yet. So how
do I share my screen?
Do you see the arrow share content next to the setting? My settings. I don't know if your screen is mine. There's an arrow on the bottom right of your screen. If you put your mouse over it, it's share content.
Oh yeah, settings.
Okay. Right, you choose the second one to share your screen or application.
For which one?
The second one, you see application / screen.
Oh yeah, see it.
Okay.
Got 27 ready. Try to explain 4x minus 3y to the power of 4.
Oh, hold on. Oh, this was Tom's, right?
Yeah, I was going to present 15, but someone did it already.
Okay, so I thought that you're going to do multinomial. No one is going to do multinomial. Okay, go ahead.
I did the binomial 1.4. There's another question underneath it. It's binomial ones. 29.
Have you done anything about? Oh yeah, show 29.
I didn't finish it for 29.
Okay, let's see. We'll finish together because that's, because the presentation serves as a review of the previous material. Binomial is in pre-calculus.
Oh, let me take a screenshot first.
Okay.
Of my notebook. I think this one is it.
Okay, so I yet can present 4x minus 3y plus 1 square. Okay, later. Let's see how yes 29 first. Because surely multinomial theorem will appear on your first exam.
I got this one ready. It's like having the formulas. The first one is like 4 and the rest is 0.
Yeah.
So
right.
You only got like x1 to the power 4, and the second one is for choosing 3, 1.
Hold on
0.
a second. What I would do is I would finish the, finish the spots before, because you have n1, n2, n3. Now you let n1 be 4. You gotta give n2 a chance to be 4. Then you gotta give n3 a chance to be 4. So you have 4 out of 4, choose 0, comma 4, comma 0. Then that would be x2 raised by 4. Then you got to give n3 a chance to be 4. You have out of 4, choose 0, comma 0, 4, right?
So
I would follow that order. I would start with 4,
0, 4,
4, 0, yes.
Like this.
Right.
And then.
Then.
I have it here.
The 2x.
Below it.
Oh, you did later. Oh, you didn't follow that order. Oh, you have your own order.
My own.
4, 0, 0.
And this is a lot.
2, 2, 1, 0, 2, 2, 0. What's the second one?
Which one?
This one. You cannot see my. No, the next to 4, 0, 0.
4, 0. Oh, it's 0, 3, 1.
0, 3, 1. Oh, that's a 0, 3, 1. Let me make this a little bit bigger. Oh, no, 3, 1, 0. So your second one is 3, 1, 0.
Yeah, 3, 1, 0.
Then you have
3,
4,
0, 1.
3, 0, 1. All right.
And then going to.
Then you have 2, 2, 0.
And then 2, 1, 1.
2, 0, 2. Which order you're following? You're jumping around.
I'm following like the highest one to the keep on going to the lowest one. I have the front ladder is like the biggest first, then the second biggest.
You do n1 first. You do n1 first, basically, right?
Yeah.
So n1 to be 4, to be 3, to be 2, to be. Yeah. Oh, I see it. Now I see your order. Okay. Okay.
And then right here, that's what I have it.
So how many terms in the end do you have? You didn't simplify. You should simplify. That's why you were saying you didn't finish.
Yeah.
Yeah, but once you get this, once you understand the multinomial theorem, so that the rest is just a little bit of calculation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. How many terms should we have? Should be total. Oh, just saying should be 15 total. I don't really know it. Because this one has a 3. Each one has 3. More than
16 terms.
So this is 12. How many terms?
The first one have 4. This one.
The first one has 4.
First one is here. Oh, if I.
Have you done all the numbers?
Not yet. So.
Not yet.
That's why I'm not
Okay, let's see. 4, 3, 1, 3, 0, 1,
3 choosing 2.
2, 2, 0, and 2, 0, 2. 2, 0, 2 is here.
0, 3.
Then 2, 1, 1.
It's not.
1, 3, 0, 1, 0, 3. 1, 0, 3 is here. 1, 2, 1. 1, 1, 2. Then you're doing, okay, how many? Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 for the first one, right? You have 10 for the first one.
Yeah.
So that means 3 of them, that means, or maybe some overlap, Okay, anyway. Okay, why don't everyone try to do multinomial next time, all right? Maybe do some, oh, you know what? Ayat is going to show 4x minus 3y plus 1. Okay, good. How, yeah, good.
Okay, share application screen, camera,
Okay.
show file.
Raised by 2 is much easier, much doable.
Okay, this one, do you see, right?
Yeah.
Okay, 4x minus 3y plus 1 to the power of 2. So we have 1, 2, 3, 4, 5, 6 terms. To choose 2, 0, 0, to choose 0, 2, 0, to choose 0, 0, 2, then to choose 1, 1, 0, to choose 1, 0, 1, and to choose 0, 1, 1.
That's all the combination, right?
Yeah.
Yeah, because it's only raised by 2. Okay, yes, good. Okay, show us your calculation.
Okay, so first one, 4x, this first term applied to the power 2. Then minus 3y and 1 applies to power 0. That's for the first term. Second term is 4x to the power 0, then minus 3y to the power 2, and 1 to the power 0, which is 1. Okay, for the third term, 4x to the power 0, minus 3y to the power 0, and 1 to the power 2, which is 1. Okay, for this term, 4x to the power 1, minus 3y to the power 1, and 1 to the power 0, which is 1. And here is the 4x to the first power, then minus 3y to the power 0, and 1 to the power 1. And the last term, 4x to the power 0, multiplied by minus 3y to the power 1, and 1 to the power 1. And that's all simplifies to this equation.
Very nice. Anyone has any questions? To make sure you can apply multinomial theorem. Okay, normal binomial theorem. Binomial theorem is for pre-calculus class. All right, thank you, Ayat. Okay, so do all of us present? Anyone else? I think Yinping or Tom, maybe if you can do another question. Or Yinping.
Yeah, I'm here.
Okay.
Can you see my screen?
Yes.
My question is 11 for the the question is in how many ways can 3 novels, 2 mathematics books, and 1 chemistry book be arranged on a bookshelf? If A, the books can be arranged in any order, the total number of books in the bookshelf are 3 plus 2 plus 1 is 6. So the number of arranged in any order is 6 factorial is 720. For the question B, the mathematics books must be together and the novels must be together. Since we have 2 mathematics books and we need to put them together, so the number of ways to get 2 books together is 2 factorial. It's the same to 3 novels. There are 3 factorial ways. Finally, the 1 chemistry book need to put on with 2 kinds of books. So there are 3 factorial ways. By the principle of counting, the number of ways is 3 factorial times 2 factorial times 3 factorial is 17.2. And for the question C, there are 3 factorial ways to put 3 novels together, and we need to put the novels with the other 3 books. So the total number of ways is 3 factorial times 4 factorial. The answer is 144. And that's
All right. Yeah. Okay. Nice. That's everybody, right? Okay, so here. Okay, so get ready for next class to present. Hopefully some of us pick some multinomial to present. And today we're going to get into probabilities. So we're going to get familiar with terms first. Some statistics terms. Okay, so chapter 2, Axioms of Probability. And because we're dealing with big data now, so probability just makes so much sense with the big data. So let's see this chapter. So we'll cover 7 sections. So introduction, sample space events, second section, axioms of probabilities, simple propositions, sample space having equally likely outcomes. A lot of times we'll assume this, that's in section 5. And then probability as a continuous set of functions, that's very interesting. So we'll see later on, we have probability models. So when we apply life applications, we're looking for some probability models to fit in. Then probability as a measure of belief. All right, so we're going to cover this. So introduction, in this chapter, we introduce a concept of probability of an event, and then show how probabilities can be computed in certain situations. All right. So let's get familiar with some concepts. The first one, sample space, right? Is known as the sample space of experiment, is denoted by S, this capital letter S, so sample space. So first one, if the outcome of an experiment consists of the determination of the sex of a newborn child, well, we assume there are only 2 genders, right? We assume there's only girls and boys, no any other gender. So the sample space will be only, either girls or boys. The baby was born either a girl or a boy. Where the outcome G means the child is a girl and B is a boy. So the second example is, if the outcome of an experiment is the order of finish in a race among the 7 horses having post positions 1, 2, 3, 4, 5, 6, and 7, then the sample space, look at this, all 7 factorial, so permutation, because Right, because it's just a permutation. The order matters. You know, if it's the first position, second position, third position, the order is important. So all 7 permutations. Three, if the experiment consists of flipping 2 coins, then the sample space consists of the following 4 points. What does T represent? Or tail. T represents, usually we use a capital letter. So we have a head, so both land as heads. Then we have a head, one is a head, one is a tail, or one is a tail, one is a head, or both are tails. Right? If we flip 2 coins, the land could be these 4 outcomes. So the sample space basically is a set of all outcomes. So 4, if the experiment consists of tossing 2 dice, then the sample space consists of 36 points. Why? Because each die has 6 sides, right? 1, 2, 3, 4, 6. Then we could have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. We could have a 2, 1, 2, 2, 2, 3, 2, 4. So it's a 6 by 6. So 6 by 6, 36 outcomes. If the experiment 5, if the experiment consists of measuring, this is continuous. So we're going to talk about the variables, you know, discrete or continuous. For the first 4, it's discrete, right? For 5, continuous. Let's see, this experiment consists of measuring in hours the lifetime of a transistor. Then the sample space consists of all non-negative real numbers, right? So X can be from 0 to past infinity, this many hours. It's continuous. Continuous, we're going to talk about the continuous variable. Let's see, you know, sometimes we make experiment of waiting for a bus, how long you have to wait for a bus to come, stuff like that. With measurements and this kind of variables, we can only measure it. We won't be able to count. If we can count the outcomes, that's called discrete. Right? We can count 1, 2, 3, 4, 5. But like time, we cannot count. So what do? We measure. Right? Like a human's heights, we cannot count. We measure. Stuff like that. Like a person's weight, we cannot count. So we measure. So any subset E, we use E to present an event. So S represents the sample space. E represents the event. So any subset of a sample space we call event. All right. See, in this case, right, we could just pick 2 from here. That would be 2 events. And this is an event. So this outcome. So sample space and an event. In other words, an event is a set consisting of possible outcomes. If the outcome of experiment is contained in E, then we see that E has occurred. And of course, can be, so when we talk about set, how many subsets a set could have is 2 raised by the number of members in it. Let's see, in this case, well, for this continuous one, we won't be able to do that. For this one, we have 36 of them, right? So the outcome, we have 36. So the subset of this will be 2 raised by 36. This will have 4 members. A subset we can make is 2 raised by 4. Okay, we also have an empty set. And the sample space itself is a subset. So we have 2 raised by the number of members in the set. So let's see in the example 1. If the event you know, the newborn is a girl. So E is the event that a child is a girl. So that's what we call the event. That's the event. Similarly, if E equals to B, this is a typo. Right? If the event equals to B, this is a typo. If the event equals to B, that means the child is a boy. That's the event. In example 2, if E equals to all outcomes in S starting with a 3, was sample 2, right? So 7 positions. Then E is the event that horse 3 wins the race. In sample 3, if event equals to head-head, so you know we did the experiment and it landed head-head and head and tail. Right? So event equal to this. Then the event E is the event that a head appears on the first coin. It could be head-head and head-tail. In example 4, event could be, so this is just give us one example, okay? One example. We could have 2 raised by the number of members, that many subsets. So what about this one? This was, we see one, the first dice is 1, landed, the second die landed 6, 2, 5, 3, 4. So that means the sum of the 2 dice adds up to 7. So that's the event. The event E, event is the sum of the dice equals to 7. And also from another end, we could think event is something we are interested in. Sometimes, you know, we look for probabilities of some events. In example 5, event could be X goes from, so the hours of 5, what's 5? Oh, the lifetime of a transistor. If the event is the lifetime of transistor is up to 5 hours, right? For any 2 events, E and F, oh, that's why they use F here. For any 2 events, E and F of a sample space, S, other books you may see E1, E2, because, you know, people like to use E1 first event, E2 second event, but this textbook is new to me too, okay? So use E and F. So if the 2 events all from sample space S, we define the new event E union F to consist of all outcomes that either in E or in F. The union, this is the union sign. Union means or. Union means or. Means the word or. So the event E union F will occur in either E or in F. All right. So in either one. For instance, in example 1, if if the event is a girl, is the event that the child is a girl, and F is the event the child is a boy, then E union F equals to the sample space, because the sample space only has these 2 outcomes. So equals to G and B, girl and boy. So it's the whole sample space. In example 3, if the event is the first one is head, F represents the second one landed head, then E union F is also the whole sample space. So E union F, right? We just call the union of event E and event F. The union of event E and event F. So similarly, for any 2 events, E and F, we may also define new event EF. What does this mean? This means intersection. This is also the textbook uses differently. Usually, intersection, we turn this upside down, turn this union upside down to represent intersection. But this textbook, I guess they just use EF. Looks like a multiplication. So EF is called the intersection of E and F, which means the outcome is in E, also in F. So the outcome in both, all right? Because it's end, intersection. Yeah, a lot of times other textbooks use this. So E intersect F. All right, but just be careful. This textbook uses EF. Let's say in example 3, if E is HT, TH, and F is HT, TH, TT, so what happens, which outcome is in both? We see H, T and T, H, right? H, H is only in E, T, T is only in F. So the intersection, so if we do the union, that would be the total sample space. If we do the intersection, only H, T and T, H, because H, T is also here. So E intersection F, intersect F is H, T, T, H. Let's see example 4. If the event is 1, 6, 2, 5, so adds up to 7, so the 2 die adds up to 7. And the F is the event, the sum of 2 die is 6. Then the intersection contains nothing. Contains nothing we call empty set. We use this notation. Looks like a big O, you know, we slash it through. So this is called empty set. Okay, empty set. Usually the first subset of any set is empty set. Means, you know, it's nothing in it. It's empty, but it's a set. So which means it contains no outcomes, right? It's an event. Event contains no outcomes. So if E intersect F is empty, we call E and F mutually exclusive. Mutually exclusive, right? Like a girl and a boy. You know, we only assume the sample space of a child to be, the gender of a child to be a girl and a boy. So the event to be a girl and the event to be a boy are mutually exclusive. So you cannot be a girl at the same time to be a boy. So we define unions and intersections, more than 2 events in a similar manner. So, okay, now we call E2, E1, E2, E3, so on up to En, all right? And the union of these events we denoted with the union, this big union, big U, and goes from 1 up to infinity, En. So in this case, the infinite many events, all right? Or this could be N, right? It could be some other, the infinity sign could be other numbers. So that means we'll have finite many events. Like the girl and the boy, right? We could have finite many events. And similarly, we use this notation to denote the intersection. Intersection, which means, you know, it happens, the outcome happens in all the events. So for any event E, we use this E raised by C, the little c like a power, right? Like in the exponent of E, we call complement. Complement. So E union E complement will be sample space, right? So we define, so EC is called the complement of E, okay? Complement of E, right? So if E is an event, let's think about a child born to be a girl, right? That's an event. Then what's the complement of the event? The rest of the sample space, which is a boy, a child born to be a boy. Right, then, so E complement it's a complement, right? So if outcome in E complement, it will not be in E. If it's outcome in E, it will not be in E complement. So I would write, so E union E complement equals to S, all right? Let me write in the chat. Oh, it's also difficult to write. So just remember this. If you can write, if you want to write as a note, E union E complement equals to sample space. And the E intersect E complement is an empty space because they don't have nothing in common. We also use this notation to represent empty set. So the complement of a sample space is empty set. That's interesting anyway. Because this is not a mathematical idea. Because mathematical idea, the first subset of S is empty set. So I'm doubting this one. Okay, don't write this one. Don't write this one. But the two things are true. E union E complement is sample space, and the E intersect E complement is empty space. So let's say we have two events. If all the outcomes in E also in F, then we see E is contained in F. So we use this notation. Okay, E contained in F. Or E is a subset of F. Usually this signs for subset. E is a subset of F. Equivalently, if all the outcomes in F also in E, we do this way. We do here. Oh. No, it's nothing changed. We just flip around, all right? Is that we do F contained in E. It says sometimes we use this. I personally never use this. So just let's make a convention. We're all going to use this, okay? E is contained in F. If we want to show F is contained in E, we will write F contained in E. So let's just agree upon with this sign. If all the outcomes in E also in F, all the outcomes in F also in E, we see the two events are the same. So far what do we have? We have E union F, E intersect F, and E complement, empty set, and also E is contained in F. So E union F equals to F union E. E intersect F equals to F intersect E. So order doesn't matter. So call this commutative loss, associative loss. So if we have three events, right? And if it's a union, if it's a union E union F union G, we can union, any two first. We can union so we can pick any two events to union them first to union. So it doesn't matter which two you union them first, all right? But the intersection we have to be very careful. So E intersect F, intersection is okay, but it's when we mix them, it's different. If it's all intersection, the order doesn't matter either. If it's all union, if we have a finite many events, we union all of them, the order doesn't matter. If we intersect all of them, the order doesn't matter. But look at this. If we have a union and an intersection mixed, so in this case, we have E union F, then intersect with G. So that matters. All right, so what does this equal to? This equals to E intersect G, union F intersect with G. And we call this distributive loss. All right, be very careful with this. So when union and intersection mixed in one, we have to be careful. So this is E intersected with F first, then union with G. Right? Then union with G. So what do? We distribute G. So we do E union with G, then intersect with F union with G. Right? I think this is called De Morgan's law. But anyway, we'll see later. There's something we're going to use Venn diagrams. All right, a lot of times we show something, we use Venn diagrams. Venn diagrams are circles to indicate union, intersection. So this rectangle represents a sample space. Right? We have two events, right? Event E, we have event F. Right? The union is this. The shaded, you see E is shaded, F is shaded. So this is E union F. Intersection is only the common ones. Is in E, also in F. So this is E intersect F. E complement. So everything not in E is in E complement. And the E union E complement is the whole sample space. And we call those grams Venn diagrams. Right? Venn is someone's name. So E is contained in F. We see clearly from this picture, right? So F is this, and the E is inside of F. So that's E contained in F. So I have E, F, G, right? So the shaded region is E intersect with G, right? E intersect with G. And this is F intersect with G. F intersect with G. Even we have three sets, or we have three events. What about this one? This one we see, this one is E union F, then intersect with G. And we know that that's E intersect with G, union F intersect with G, right? You see clearly that's E intersect with G, that's this one. Then F intersect with G, that's this one. So putting these two together, that's a union of it. That's a union of these two. That's a union of E intersect with G and F intersect with G. Let me know if anyone has any questions. De Morgan's law. Okay. This is De Morgan's law. De Morgan's laws are very important, those two. Okay, let's see this. This is saying the complement. So this C represents the complement. The complement of union of all n events, because E1, E2 up to En, the union of all the n events, the complement of the union of all the events equals to the intersection of all the E complements, the events complements, this intersection of the complement of all the events. All right. So this takes some time to sink in. I remember when I learned this, you have to do some homework to let this idea to sink in. So basically the union of the complement equals to intersection of the complement, all right? And so vice versa, the complement of the intersection equals to the union of the complement. Let's say two events. Two events is easier to see it. Right? If we have E union F, the complement of it, the complement of E union F, we see that's E complement intersect with F complement of F. Right? So the complement of union equals to the intersection of the complement. Then the complement of the intersection equals to union of the complement. So EF, E intersected with F, the complement of intersection of EF equals to the union of E complement with F complement. Or I should say complement of E, complement of F. All right. So complement of union equals to intersection of complement. Complement of intersection equals the union of the complement. We could use a Venn diagram to prove this. So this is proof of this. All right, let's read this proof. To prove De Morgan's laws for general N, suppose first that X is an outcome. So X in here, then X is not contained. So if X is in the complement of the union, no, X is in this, X is in the complement of this union, then that means X will not be in the union, because the union and the union complement, right? So not be in the union, because if it's in the union complement, of course it's not going to be in the union. If it's not contained in the union, that means it's not contained in neither, right? Not contained in all of them, in any of them. So X is not contained in any of the events, which implies X must be contained in some complement of the events, right? And also, it must be contained in all, because it's in none of these events. If it's in none of the events, it has to be in all the complements. So X is contained in all the complements. That's why we have the union of the complement. So the complement of the union is the intersection of the complements, because it's in all the complement of the events. So that's why it's in the intersection of all the complement. So basically, that's just logic, right? It's logic. To go the other way, suppose X is an outcome in the intersection of the complement of events, right? If it's in the intersection, that means it's in all the complement of the events. The X is contained in all the event complements, which means X is not contained in none of any of these events, which implies X is not contained in the union, right? Because it's not in any of the events. Of course, it's not going to be in the union of the events. So in turn, implying that X is contained in the complement of the union. So this proves the first De Morgan laws. De Morgan laws is very useful, right? To prove the second, we use the first law to obtain this. So the complement of the union, because now we use the complement, right? We just use the idea. The complement of the union equals the intersection of the complement. But inside the events is complement of events. So we have this complement. Well, what's complement? Double negation. It just goes back. It's just the intersection of all the events, right? Then we can take a complement from both sides. So union of the complement equals to complement of the intersection. Anyone has any questions? Okay, axioms of probabilities. One way of defining probability of an event is in terms of its long-run relative frequency. Such a definition usually goes as follows. We suppose that an experiment whose sample space is S is repeatedly performed under exactly the same condition. you know, which for statistics, a lot of times we have to assume for each event E of the sample space S, we define N of E to be the number of times in first N repetitions of the experiment. So, okay, be very careful. We have to synchronize the notation. So N of E, so the definition is the number of times in the first N repetition of the experiment that event E occurs. So let's use an example. Let's say I'm tossing a die. Let's say in the hospital, right? Children are born. So maybe just one morning. So we want to count how many girls to be born in the morning. Set up a time. So we counted, okay, 5. So 5 girls. So we have 5 events. So N of E would be 5. Okay. So N of E record the repetitions of this event occurs, the same event occurs. And P of E is the probability of the event occurs. Right, so probability. So what is that? Let's think. The sample space of a child born to be a girl and a boy, right? Only 2 sample spaces is 2. What is the probability of the child born as a girl? Right, we know it's 50%, right? 1.5. So that's a probability. So it's defined as this. Wow. Okay. So probability of event E occurs is defined as the limit of the number of times of E occurs divided by N as N goes to infinity. As N goes to infinity. Hold on 1 second. They're using 2 same N's. You see this N of, so this N is N of the event E occurs, but this N, why they use 2 same N's? This N represents a number goes to infinity. Okay, just don't mix up with these N's, 2 N's, all right? So N of E represents the number of the event occurs in the repetition. So event E, right? Event E in the experiment. How many times event E occurs? But this denominator N is as N goes to infinity. So let's see this. So P of E is defined as the limiting proportion of time that E occurs. It's thus the limiting relative frequency of E. All right, so this is something new I learned from this book. Let's see this. Let's see. So this is saying, how do we know that N of E divided by N will converge to some constant limiting value that will be the same for each possible sequence repetition of the experiment? For example, suppose that experiment to be repeatedly performed consisting of flipping a coin. How do we know that the proportion of heads obtained in the first N flips will converge to some value as N gets larger? All right. Okay. Now this N makes sense. So this N of E is the number of times event E occurs. This N is the number of experiments. All right. The number of experiments. Also, even it is Even it does converge to some value, how do we know that if the experiment is repeatedly performed a second time, we shall obtain the same limiting proportion of heads? Proportion of the relative frequency definition of probability usually answer this objection by stating the convergence of n of e over n to a constant limiting value is an assumption. Statistics, probabilities, we do a lot of assumptions, or the axiom. That's why we will learn some axioms. Here we have time of the system. However, to assume that n of e over n will necessarily converge to some constant value seems to be an extraordinary complicated assumption, for although we might indeed hope that such constant limiting frequency exists, it does not at all seem to be a priori event that this need be the case. In fact, would it not be more reasonable to assume a set of simpler and more self-evident axioms about probability and then attempt to prove that such a constant limiting frequency does in some sense exist? The latter approach is the modern axiomatic approach to probability theory that we shall adapt this test. Okay, all right. So, right, this textbook is explaining why they adapted the following axioms. In particular, we shall assume that for each event E in the sample space S, there exists a value probability of E referred to as probability of E. We shall assume that all these probabilities satisfy a certain set of axioms, which we hope. Okay, all right. So now consider an experiment whose sample space is S. Okay, by convention, we use S. For some event, for each event E of the sample space S, we assume that a number probability of event is defined and satisfies the following three axioms. So axioms serves as the foundation of something. All right. So probability is three axioms of a probability. Otherwise, we wouldn't be able to even talk about it, right? So probability survives in between 0 and 1. 0% and 100%. Right? Something could happen, something could never happen maybe, or could happen all the time. That's it, in between of those two. Right? So probability survives in between 0 and 1. And the probability of the sample space is 1, right? The whole sample space is 1. It's 100%. Then 3, for any sequence of mutually exclusive. Remember what's mutually exclusive? You know, a child to be born to be a girl or a boy, right? Even to be a boy and even to be a girl are mutually exclusive. Mutually exclusive. But in this case, you know, the girl is a complement of boy, the boy is a complement of girl, because we only have two outcomes. But usually we have E1, E2, E3, you know, up to N, many events, all right? So maybe they're all mutually exclusive. So for any sequence of mutually exclusive events, E1, E2, so on and so forth, which means mutually exclusive means, you know, the intersection is empty. The intersection is the empty set. Right? Intersection of any two different events, or the same events, the intersection is itself. Different events, the intersection, mutually exclusive events, the intersection is empty set. So probability of union of all the events equals to sum of all the probability events. So this actually goes up. This build up in between of this, right? As up to 2, because this includes all the outcomes. So basically, this is the sample space, right? So probability of the sample space equals to the probability, the sum of all the probabilities of events, right? Think about Use a girl and a boy as an example, right? Probability of a girl is a half. Probability of a boy is a half. Half plus half is 1. So probability of the sample space is 1. All right, so we call P of E as the probability of event E. Okay, probability of event E. But with mathematics, we can read as a P of E, all right? Yeah. So, we can have some, so from axiom 3, we could have this probability of a sample space equals sum of all the probability of events. And so probability of empty set equals to 0. So this is interesting. This is new to me. So this is saying, so this is, that's why before we have the complement of a sample space is its empty set, right? So we just, we just use this as convention then. So probability of empty set is 0, right? But because this is no event, probability of, not interesting in any event is 0. Because this is different from pure mathematics, right? Pure mathematics counts everything. So this is saying we're not interested in, sitting there doing nothing. So that is the no event. No event. So no, NULL is a mathematical word, right? So basically, nothing happened. Has a probability 0 of occurring. So which means, we would be always talking about some events. Even nothing happens, we're going to treat it as an event itself. So note, it follows that for any finite sequence of mutually exclusive events, E1 up to En, of course, this is true, right? It's the same idea. Okay, probability of uni of all the EIs, which is the sample space, right, equals to probability. Oh, okay, it doesn't have to be the whole sample space because this will go up to N only. We just pick up to N events. Then the uni of probability equals to probability of each adds up. Okay, we still have time. All right, so let's finish this. Let's see this example. If our experiment consists of tossing a coin, and if we assume that the head is as likely to appear as a tail, then we would have probability of head and equals the probability of tail equals half, because it either land as head or tail. On the other hand, if the coin was biased, right? Biased means the coin is not, it could land on the side or something else. And we believe that a head was twice as likely to appear as a tail, then we would have something. But for us, we don't use this, okay? We assume coin is a fair coin. If a die is rolled and suppose that all 6 sides are equally likely to appear, then we would have probability of getting 1 equals the probability of getting 2 equals the probability of getting 3, so on and so forth, and each is 1 out of 6, right? 1 out of 6, because the sample space will have 6 different things, so 1 out of 6. From axiom 3, it would thus follow the probability of rolling an even number would equal the probability of getting 2, 4, 6 uni, right? Probability of getting either 2 or 4 or 6 is the probability of getting 2 plus probability of getting 4 plus probability of getting 6, which is a 3 over 6, which is a half. Okay. The assumption here The assumption of the existence of a set function P defined on the events of a sample space S and satisfying axioms 1, 2, 3 constitutes the modern mathematical approach to probability theory. It's hoped that the reader will agree that axioms are natural, okay, and in accordance with our intuitive concept of probability as related to chance and randomness. Furthermore, using these axioms, we shall be able to prove that if an experiment is repeated over and over again, then with probability 1, the proportion of time during which any specific event E occur will equal P of E. This result is known as the strong law of large numbers. So we'll learn the law of large numbers. Statistics is a science nowadays. It's based on 2 theorems. So 1 is the law of large numbers, and is presented in chapter 8. In addition, we present another possible interpretation of probability as being a measure of belief. That's something else. Technical remark. We have supposed that the P of E, or probability of event E, is defined for all the events E of the sample space. Actually, when the sample space is an uncountable infinite set, probability E is defined only for a class of events called measurable. All right, measurable sets. That's something we don't have to worry about. However, this restriction need not concern us. Yeah, that's a higher level of probabilities to concern, if it's measurable or not. Okay, anyone has any questions? So next class we'll talk about, some propositions. For today, just get used to the terms, sample space, events, and De Morgan laws, and complement, union, intersection, and these 3 axioms. All right, probability is in between 0% and 100%. Right, tomorrow is raining day or sunny day, right? The probability can, tomorrow to be a sunny day, the probability can only be up to 100%, cannot be 110%. Probability of a sample space is 1, which also this equals to probability of all the events. That's here, axiom 3. The union of all the events, the probability of the union of all the events equals to the sum of the probability of events. Okay, that's all I have to cover today. Anyone has any questions? If no questions, you are free bird. You can go ahead studying to do your homework. So homework 1 we'll do in 1 or 2 weeks. All right. So maybe just in 1 week, is it okay? I change the due dates in 1 week. Assignments. Okay, you know what? I give it 2 more weeks for homework 1, all right? So I'm going to change the dates to be 2 weeks later. Oh, I already changed. Already did. So 2/14. Okay, so that's already done. All right, I'm going to